SwayamPrabha. Digital India. Educated India.
So, welcome to the next lecture in the course of rapid manufacturing, which is focused towards rapid prototyping processes. Photopolymerization material. Here we will see the application of a UV curable resin in the display panel of cell phones. So, in cell phones display panel we use UV curable lasers. So, you can see here these are the cross sectional view of the display panel. So, here you can see end seal of the liquid crystal panel is done here. So, it has a UV curable resin. Then you have a liquid crystal here, this is liquid crystal. Then for protecting the connection of FPC and ITO you have this. So, the UV curable resin is also filled here. So, it has low moisture permeability and repairable properties are here. Then when you talk about the main sealing, this is the main sealing of liquid crystal panel, that is also having a UV curable resin. So, it is very clear from this figure that UV curable resins play a very important role. Okay, it is transparent and it also has low moisture permeability. The important property of the entire photopolymerization is the reaction rate. Because how quickly does the reaction happen such that the liquid is converted into a solid. You can make it in one shot, liquid to solid, or liquid viscoelastic nature and then solid. Suppose if this takes a slow duration of time, the best part is going to be between spots, it is going to gel and form a line very good. If it is instantaneously curing, you might not get the gelation very well, and when you talk between layer to layer, again there can be a possibility of delamination. So, in that case reaction rate plays a very important role. As it is evident, the photopolymerization reaction in stereolithography resin is very complex and important. Because if the reaction rate is very slow, then the shrinkage might be very high. To date, no one has published an analytical photopolymerization model that describes reaction results and reaction rate. However, qualitative understanding of the reaction rate is straightforward from simple formulations. Broadly speaking, reaction rates for photopolymers are controlled by concentration of photoinitiators and monomers I and M. So, the rate of polymerization is the rate of monomer consumption, which can be shown as Rp equal to differential of M by T. So, this is the rate which is directly proportional to M. M is the monomer and Ki to the power half, okay, or this can be written as M root Ki. That is a function of radical generation efficiency, the rate of radical initiation. Hence, the polymerization rate is proportional to the concentration of monomer, but is only proportional to the square root of the initiator concentration. This is a very important point. So, what is the effect of the initiator concentration with respect to monomer? Using the similar reasoning, it can be shown that the average molecular weight of polymers is the ratio of the rate of propagation and the rate of initiation. Rate of propagation means how quickly the networking is getting formed, and the rate of initiation is how quickly it is getting, this is forming a network propagation, this is how you are initiating it. So, the average weight which is otherwise called as kinetic average chain length VO can be written in terms of Rp by Ri. Okay. Ri is the rate of initiation of the macro monomers. Both the equations has important consequences as well as a cell process is concerned. Higher the rate of polymerization, faster can be the build time. Build time is very important. Today, if you want to have a very high resolution rapid prototyping made, it might a small 1 cubic centimeter volume can take almost close to 4 or 5 hours. If you have a very high resolution where the features are very small, you will get this. Since SL resins are predominantly composed of monomers, the monomer concentration cannot be changed much. So, this is also important thing. Monomer concentration cannot be changed much. Hence, the only other direct method of controlling the polymerization reaction and the kinetic average chain length is through concentration of the initiators. They are sometimes very crudely called as catalysts. This can be changed. However, the first and the second order equation indicates a trade-off between these characters. Doubling the initiator concentration only increases the polymerization rate by 1.4 times, but reducing the molecular weight of the resulting polymer by the same amount. So, strictly speaking, this analysis is more appropriate for acrylate resin since epoxy continues to react after laser exposure. So, second equation does not apply well for epoxies. However, the reaction of the epoxies is still limited. So, it can be concluded that a trade-off does exist between polymerization rate and the molecular weight of the epoxy resin. So, molecular weight of epoxy resin is proportional to polymerization rate. Okay. So, molecular weight, you can try to play with the molecular weight and then try to get the polymerization reaction. So, now let us understand more in detail about the process called stereolithography. Stereolithography is a process wherein which we use a liquid photopolymer where the process of polymerization happens. Okay. We use a laser which is a UV laser. So, this UV laser, the lambda is very important, the power density is very important. Power density is nothing but power applied per unit area. So, this is nothing but the focusing. Okay. And this lambda is the energy photon. So, the laser energy is divided into photon energy. Photons are packet of energies in the light. So, photon energy is equal to h by lambda. So, now you can see what will be the influence of photon energy. This energy is per photon energy. Okay. Depending upon the wavelength, the photon energy can increase or decrease. Fine. So, this is very important. So, power density is also important. For power density, we play with the lenses. So, it straight passes and here is said as XY scanning mirror, which is nothing but a galvometer. You can see here this is attached to a motor. This motor is controlled by pulses. So, you can see stepper motor, this motor will be attached to a shaft and this is controlled by steps. So, this controlled motor can be used to control the rotation of this mirror. This mirror in turn reflects on top of the liquid polymer. The liquid polymer is placed inside a vat. Okay. This vat is placed on top of a table. This is a build platform or a table. So, this table is lowered and highered by a elevator. So, again here you will have a stepper motor attached, stepper or servo motor attached. So, this resolution tries to dictate the resolution of the layer. So, after one layer of exposure, the table, the built platform sinks down. So, the next layer is of liquid is formed on top. As I said, where there is a doctor's blade, we have a sweeper. The function of the sweeper is to make sure that there is a uniform layer of liquid on top of the built area, built platform. Okay. So here 2-3 things you have to note. The density of the layer is directly proportion. So there is something called as density of the built layer, okay, is directly proportion to the hatch pattern. You can establish two different types of, you can establish close hatch pattern or open hatch pattern. So basically open hatch pattern gives you only a shape to the layer. For example, you can have a layer, this is open, okay. You can have a layer which is closed, the closed layer. So closed layer will take more time, closed layer is heavier, closed layer is stiffer, but if you just wanted to use it as a supporting layer or supporting part, then you use this open structure and start building it. Okay. So this is about the stereolithography process, and here you just by changing the density of the built area, you can try to make certain portions weaker, so this weaker portion can be chiseled off as and when you start growing it. The stereolithography creates a solid part by selectively solidifying. The selective word is a very big word, and the laser gives you the freedom of doing selective. So wherever I wanted to cure, only those portion will be cured. For example, if you have a layer and you have two islands, okay, only these islands have to be cured. It is possible, rest all you don't even have to touch, possible. Or two islands alone not to be touched, rest all layer has to be touched, possible. So it will cure. So it is selective solidifying a liquid photopolymer resin using a UV laser. That is stereolithography. As with many other rapid manufacturing processes, the physical part are manufactured by fabricating cross-sectional contours or slices, one on top of another. For example, I have a shoe, okay. So I make this as layer by layer by layer. This is what we are saying. So fabricating a cross section contour or slice one on top of another. These slices are created by tracing 2D contour of a CAD model in a vat of photopolymer resin with a laser. The part being built rests on the platform that is dipped into the vat of resin as shown in the schematic diagram in the previous slide. After each slice is created, the platform is lowered, the surface of the vat is recoated, then the laser starts to trace the next slice of the CAD model, building the prototype from the bottom up. So you are trying to build the part from bottom to top. That is what is called as bottom up approach. A more complete description of SL process may be found in. So the creation of the part requires a number of key steps. One is input data. Basically the input data comes from 3D solid CAD model. Okay. Then what we do is we try to make the part preparation. Then we try to do the layer preparation. And finally, the laser scanning in the two-dimensional cross-section in each slice is carried out. The input data consists of STL created from a CAD file or reverse engineering data. Input CAD file. This CAD file, as I told you, has to be a solid model, not a surface model. Predominantly we go for solid model, 3D solid model, or reverse engineering data, point cloud data or MRI data, CT data. That's what we are saying here. Part preparation is the phase at which the operator specifies support structures to hold each cross section in place while the part builds and provides values for machining part. For example, let us assume a person who is hanging. Okay, you are trying to reconstruct him using the SL process. So you see here there is a overhang of his hand on both sides. This, if you have to cure only in the top layer, it is not possible. So what we do is we first see how do we support this layer from the bottom. to this area, and then when it comes to this height or this level, you see that the UV laser falls on it and then creates it. These parameters control how the prototype is fabricated in the SL machine. Layer preparation is the phase in which STL model is divided into a series of slices. So, what is this STL model? When you finish the CAD, you store the CAD data as star.stl. So, star.stl, when you store, it becomes a STL model. So, STL model is nothing but you try to convert the solid model into testellations. Testellations are small triangles or meshes which we call. So, it is converted into that, and the STL model is then further divided into a series of slices as defined by part preparation phase and translated by a software algorithm into a machine language. Why are we talking about software algorithm and machine language? Machine here will try to give you the feed rate, the other machine parameters, but the software will only slice and give you the data. This information is then used to drive the SL machine and fabricate prototypes. The laser scanning of a part is the phase where the actual solidification happens and the layer is formed. Actual solidifies each layer in the SL machine. After building the part must be cleaned and post cured and finished. So, what happens is you will have a staircase effect which is coming up on the, because this is layer by layer by layer information. So, you will have staircase effect coming into action. So, this staircase effect has to be smoothened. Okay. So, this smoothening operation is called as post curing operation. Post curing can be heat treatment, can also be smoothing and then getting the finished part. So, during either the cleaning or the finishing phase, the SL machine operator may remove the supporting structure. What is a supporting structure? If you go back, this is called the supporting structure. Till here, it will be on both sides. During finishing, the operator may spend considerable time sanding and filling the part to provide the desired surface finish. So, this is what I said, smoothing can happen by doing this, that is basically finishing the surface, or if you want you can try to even post cure. Post cure is nothing but we do annealing or maintaining the polymer. So, here what we do, post cure, we put the polymer into a oven. Product into oven, maybe for some temperature, whatever, depending upon the polymer, and we place it at time. So, we make sure all the networking between the monomers which was initiated has to be completed. As such, in polymers 100% or 99.9% curing happens over a period of time. So, the typical SL machines have many subsystems. After the process is over, you will have subsystems. So, one is recoating system, platform system, VAT system, laser and optic system, and control system. These are the subsystems. When you talk about modular concept, this is what we were trying to talk about. Subsystem 1, subsystem 2, subsystem 3, subsystem 4, and subsystem 5. So, if you see that in this entire SL machine, if the controller is bad, so we just replace controller. So, here it also has a proper interface with rest of the machine. Okay. So, this is what is a product divided into several sub modules, and each module has a function, which I explained in the previous slides. Each module has its own function. If one function conks off, it does not have any influence on the others. So, you replace this function and then do it. And when you do a subsystem, again you have several parts in it. So, you remove and strip it off and see which part is defective, just replace that. That is how the modular concept works. So, this is we saw in detail in the previous system. So here we are only seeing the new thing is pre-coater blade. So the pre-coater blade tries to push the liquid on top of this layer when it is getting formed, so that you have a uniform thin layer which is getting formed. Now which dictates the layer thickness, or how small can the layer thickness be? Generally the layer thickness depends on the resolution of the elevator. So this resolution primarily dictates the thickness layer. The next one is the spot. Okay, what depth it goes on a Gaussian distribution. And the next one is going to be the table XY movement. So all these things dictate the resolution of the object. So liquid resin, vat, I have explained all these things in detail. Recoating is done using a shallow dip and a recoater blade sweeps. This is what I said. The process can be described as follows. After a layer has been cured, the platform dips down by a layer thickness. The recoater blade slices over the whole billet, depositing a new layer of resin and smoothing the surface of the vat. A common recoater blade type is generally called a Zifree blade, which is a hollow blade that is filled with resin. A vacuum system pulls resin into the blade from the vat. Okay, so a hollow system, hollow blade. What happens when there is excess? It sucks. Vacuum system pulls the resin into the blade, which blade is Zifree blade. As the blade translates over the vat to perform recoating, the resin is deposited in the region where the previous part cross section was built. When the blade encounters a region in the vat without resin, the resin falls into this region since the weight is stronger than the vacuum force. So you have understood. So if there is a small vacuum, or if there is a small island which is created where there is no resin, the blade encounters a region in the vat without resin. The resin falls into the region since the weight is stronger than the vacuum force. The blade alignment is critical to avoid blade crashes. When the blade hits the part being built and often delaminates the previous layer. So when the blade moves, it also moves with a certain force/speed. When it is slightly higher, when there is an undulation, it will try to hit and do. The blade gap, the distance between the bottom of the blade and the resin surface, and the speed are important variables for the user to control. Platform consisting of a built platform that supports the part being built and an elevator that lowers and raises the platform. The elevator is driven by a lead screw. Lead screw is nothing but a ball screw mechanism which is there in CNC machine. So you will have to, this decides the resolution. A vat system is simply the vat that holds the resin, combines with the level adjusting device and usually an automatic refill capability. The optic system consists of a laser, focusing and adjusting optics, and two galvanometers that scans the laser beam across the surface of the vat. Modern SL machines have solid state laser that have more stable characteristics than their predecessor. Various gas lasers were there. So solid state lasers are more efficient. So today we use NDYO4 laser. Then that output radiation is 1064 in the near infrared. Additional optic devices triple the frequency of 354 nanometer in the UV range. So we do the additional tripling. Doubling is there, tripling is there, it just divides. So you get to this. The laser has a relatively low power in the range of 0.1 to 1 kilowatt as compared with the laser used in other RM process and material processing application. So the important thing to note is laser. This laser is a NDYVO4 laser, which is nothing but a solid state laser, solid state laser, so that it has a better life and it can help to give better resolutions. The control system has three main subsystems. You have process controller, controls the sequence of machining operation. Typically, this involves executing the sequence of operations that are described in build file that was prepared for a specific part or a set of part. Process controller. Commands are sent to the various subsystem to actuate the recoating blade, to adjust the resin level, or changing the vat height, or to activate the beam controller is done by the process controller. The sensors are used to detect resin height and to detect force on the recoater blade to see whether there is any clash. The beam controller converts the operating description into the action that adjusts the spot diameter, focus depth, scan speed and other things. Spot diameter, focus depth. See, when you look of a laser, you always have a waist. So, from here to here, where this Z will be in 1 micron or something like that. So, here will be your focal plane. So, from here to here, wherever you place the focal plane, so you can shift up or down, so that you get in this distance, wherever it is, you try to get a same performance. And when you push it up, you get into defocusing. When you push it down, you get into defocusing. What is defocusing? The beam diameter is expanded. Moment beam diameter is expanded, the flux reduces. What is flux? Power density. Flux is heat per joules per millimeter square, that reduces. The environmental controller adjusts resin vat temperature, and depending upon the machine model, adjusts the environmental temperature and the humidity. The main advantages of SL technology over the other RM parts is part accuracy and finishing. These characteristics lead to a wide range of usage of SL parts as form, fit, to a lesser extent functional prototype. It is to a lesser extent functional prototype. SL machines are used for form, fit analysis. Okay, and since it is made out of polymer, and that too which is starting from liquid, the strengths are weak. So, it will be predominantly used for prototyping only. When you talk about prototyping, form fit you can use, and sometimes you can use for functional analysis also. The two-dimensional accuracy for SL machines are often quoted as the ratio of an error per unit length. For example, it is 0.002 inch by inch. So, the error per unit length is told when we talk about the accuracies. Accuracies are told in error per unit length. Modern SLS machines are somewhat better than this. The layer-based building phenomena and errors. Several phenomena should be noted since they are common to all the radiation and layer-based RM process. The most obvious phenomena is discretization. Example, a stack of layers causing staircase effect. Suppose you have an object like this, and if I have to divide it into several layers, so what I get, this is effect. This effect is called a staircase effect. Or if I draw it on the other way around, if I have a curve like this, okay, you can have, so you can see here, I have exaggerated, so you will have the effect like this, because every layer is like this, one layer stacked on the other layer, stacked on the other layer. So, when you see that, this is called as the error. Error in the object what you formed and the error in the object what you got. So, all these things are happening because of the phenomena called discretization. A stack of layer causes staircase steps on slant or curved region. In straight, you will not get this effect. Whenever there is a change in slope, you will have this. So, layer wise nature of most RM process causes edges of layer to be visible. Conventionally, Commercial RM processes build parts in a material safe mode, means that the staircase effects are on the outer side of the CAD part surface. Please note down this. Material safe mode. Outside of a CAD part surface, technicians can sand or finish part. The material they remove is outside the desired part geometry. So, material safe mode means the staircase step are on the outer side of the CAD. So, when they sand it or finish it, it's only the outside, so they get it. The other discretization example are the set of laser scans on pixel. So, when we talk on pixel, it is here, it is volume pixel. So, it is voxels. Okay. In most processes, individual laser scans or pixel are not visible on part surface, but in other processes such as fused deposition model, the individual filaments are noticeable. In SL it is not there. Okay. As the laser scans or a cross section or a lamp illuminates a layer, the material solidifies and as a result shrinks. So, in SL, shrinkage is one big phenomena which has to be taken care. When resin photopolymerizes, they shrink since the volume occupied by monomer molecules is larger than the reacted polymer. So, there is a shrinkage phenomena happening. Similarly, after powder melts, it cools and freezes, which reduces the volume of the material. So, it also happens, it is not only in liquid, this is for a liquid and the next one is for a powder. The powder can be even metal powder, ceramic powder, polymer powder, whatever. When the current layer is processed, it shrinks, pulls on the previous layer, causing the stresses to be built in the part. So, this leads to delamination. Delamination means it is breaking. Suppose I have one layer, I have another layer, something like this. So, this portion is called as delamination, breaking. This is layer 1, this is layer 2. Okay, breaking. That is delamination. I have exaggerated, just peeling off. And this the stresses which are remained are called as the residual stresses, which has a major influence on the dimensional accuracy of the part. SL scan patterns. Weaver. Prior to the development of weave, scan patterns were largely an ad hoc development. Weave. As a result, post-cure curl distortion was the major accuracy problem. The weave scan pattern became available to use in late 1990s. The development of weave began with the observation that distortion in post-curing parts was proportional to the percentage of the uncured resin after removal from the SL vat. Another motivating factor was the observation that shrinkage lags exposure and that this time lag must be considered when planning a pattern on the scan layer. This is very important. Was the observation that shrinkage lags exposure and that this time lag must be considered when planning the pattern of laser scan. The key idea in weave development was to separate the curing of the majority of the layer from the adherence of that layer to the previous layer. So, curing was to separate curing and adherence. The weave style consists of two sets of parallel laser scans. First, parallel to the x-axis, apart with a cure depth of 1 mm less than the layer thickness. Second, parallel to the y-axis, spaced 1 mm apart, again with the cure depth of 1 mm less than the layer thickness. So, this is how you form a weave styling. So, this is what is the weave styling. The weave build style cures about 99% of the resin at the vat surface and about 96% of the resin volume through the layer thickness. So built style cures about 99% of the resin at the wet surface on the top, and about 96% of the resin volume through the layer thickness. Figure below shows a typical weave pattern illustrating how weave gets its name. So this is 1 mil in X, this is the pitch between the two layers, and this is the width of one layer. Comparing with previous build styles, weave provides far superior results in terms of eliminating cure and warpage. So even though weaves was a tremendous improvement, several flaws were observed with its usage. Corners were distorted on a large surface. Microfusers occurred. It was concluded that significant internal stress developed within part during the part building, not only for curing. As a result, improvement of weave were investigated, leading to the development of star weaves. So this weave pattern had a problem, so then they went for a star weave. So this is called the star weave. We will see star weave. Star weave was released in October 1991, roughly 1 year after the weave. Star weave addresses all the known deficiency of weave and worked very well with the resin available at times. Weaver deficiency were traced to the consequences of two related phenomena: the presence of shrinkage and the lag of shrinkage related to the exposure. These phenomena led directly to the presence of large internal stresses in the part. Star weave gets its name from three main improvements: staggered hatch, and then alternating sequence, and retracted hatch. So this is weave, this is star weave, this is weave. Okay. Staggered hatch directly addresses the observed microfillets, considering figure below, which shows the cross-section view of the hatch vector between two layers. Okay. The hatch vector in weaves from vertical walls that do not directly touch, whereas in star weave the hatch vectors are staggered. So it's like stitching between two Gaussian distribution. So that is what it is. So here you see it is completely. And what is this? This is nothing but a Gaussian thermal distribution, temperature distribution. Okay, temperature distribution. Star weave, the hatch vector are staggered such that they directly adhere to the layer below. Star weave, to elevate this, alternating hatch vectors are retraced from the boundaries. So from the boundaries alone, retraced from the boundaries. So you can see these are the borders, these are the hatches which are done. So this retraced hatch is performed for both X and Y vector. So that what happens, this is like a limiting end which has on the both sides for doing it. So ACES scan patterns. So this is accurate clean epoxy solid was the answer to this needs. ACS is not just a scan pattern, but is a family of built style. The operating words of ACS acronym is accurate. Okay. So rather than achieving 96%, typically it talks about 98% curing. So it avoids internal stresses, cure and warps. So this is the scan pattern. So here are the details: varying layer thickness, you can see, hatch spacing, hatch over cure, fill over cure, blade gap percentage, sweep in time, Z waiting time and pre-dip layer. So these are the set of details for various variables which is used in SL, where ACS scan patterns are used. The vector scan microstereolithography is an advancement, when the difference between stereolithography and microstereolithography is the word micro, where the dimensions of the part whatever is getting developed is very small. Several processes were developed exclusively for microfabrication application based on photopolymerization principle, using the laser and X-ray as an energy source. These processes build complex shaped parts that are typically less than 1 millimeter in size. They are referred as microstereolithography, MSL, integrated hardened stereography, or deep X-ray lithography, and other names. In contrast to the conventional SL, vector scan technologies for the micro scale typically have moved the VAT in XYZ direction rather than scanning the laser beam in two directions. So, to focus a typical laser to a spot size less than 20 millimeter requires a laser focal length to be very short, causing difficulty for scanning of the laser. So, laser focal length should be very short. So, that is what is used in microstereolithography. So, here we use 325 nanometer, which is helium cadmium laser is used. The beam diameter is around about 0.33 and the divergence is 1.25 milliradians. Okay. It propagates 280 millimeter, then encountered a divergence lens and a convergence lens with is 85 millimeter away. So, with this what we do is we start focusing it to a very stringent spot. So, in contrast, the high resolution of microstereolithography system with laser spot size is in the order of 10 millimeter. So, here we talk about the Rayleigh effect, but these things you can read by yourself. So, the example of devices built with this method include tubes, manifolds, springs and flexible micro actuators and fluid channels on silicon for various MEMS application. Tagashi and Nakajima had demonstrated the use of this technology for connecting MEMS gear together on a substrate. The artifacts fabricated using micro SL can be used as a mold for subsequent electroplating, followed by removing of the resin. So, microstereolithography was used, and the literature it was said that Ikeda and Hirova Tari were the two who used it exhaustively. So, here are the resolutions which we talk about. These are the capabilities of the machine. So, 5 millimeter spot size of a UV beam, position accuracy is 0.25, and then minimum size of unit of hardness is 5 millimeter cross 5 millimeter. The maximum size of fabrication structure is 10 millimeter cross 10 millimeter. Mask projection, photopolymerization, technologies and processes. Mask projection. Several groups in Japan and Europe pursued mask projection stereolithography technique. The main advantage of mask projection is the speed. Since the entire part cross section can be cured at one time, it can be faster than the scanning of a laser. The dynamic mask can be realized by LCD screen, by spatial lighting modulator or by DMDs, such as digital light processing chip manufactured by Texas can be used for producing this. So, the mask projection stereolithography is much faster than the normal one. Some of the earlier utilized LCD, then it became LED. As today LED is exhaustively used displays as their dynamic mask, while another early system such as spatial light modulator was used. The remaining system uses DMD. So, the latest system uses a UV lamp which is radiated and we get it. So, commercially this technique was commercially brought by Microtech, Germany. So, they were doing this. So, they developed several of these devices for their application. Their rapid micro product development machine using helium cadmium laser enabled construction of small parts layer by layer with a high quality in the sub nanometer range and with the feature dimensions less than 10 millimeter. So, look at it, feature size is in the nanometer range. So, this is mask we have seen already. We have a broadband UV lamp. So, it is passed through a pinhole, then you have a collimating lens, then you have a filter. This filter hits at a DMD, digital micrometer device. So, you have lot of small lenses. So, these lenses whatever image comes it forms here and it tries to form an imaging lens, and this is formed on the surface. So, this is a resin vat translation stage. A computer tries to give the information through this. So, here the DMD works on the computer input. So, we do bitmaps. Bitmap information is given to the DMD and the mirrors swing, switch on, switch off, and then try to create a mask. This mask is projected onto the resin and you try to get it. So, from Georgia Tech shows this figure. So this is mask projection stereolithography technique. So you have a controller, you have a UV lamp, this is a UV lamp, you had optics, you have DMD mirror, and then you have a watt location, and then you have a stage which moves up and down. Similar to conventional SL, MPSL process starts with a CAD model of a part which is then sliced at various heights. So CAD model of a part which is then sliced at various heights. So that means to say the layer thickness can be varied. Today we talk about a technique called as adaptive slicing, where in which you can have slice like this, slice like this, slice like this, slice like this. So this is adaptive slicing, layer of varying height. Each resulting slice cross section is stored as bitmaps to be displayed on the dynamic mask. UV radiation reflects off on the on micro mirror and is imaged onto the resin surface to cure a laser. In a system at Georgia Tech, a broadband UV lamp is the light source, a DMD is the dynamic mask. Automated XYZ stage is used to translate the watt of a resin in 3 dimension. Standard SL resins are typically used in this process. So this is how the process looks like. So you can see the lens system. We have talked about the built envelope. What is the built envelope? That means to say the area within which the object can be done. Look at the resolutions what we talk about, and then pixel size we talk about in microns, and high resolution will be this. So higher the resolution, better will be the clarity of the feature, but the longer will be the time of build. You can see the layer thickness can vary from 25 millimeter to 150 millimeter. However, several of the machine models have a very important difference. They build parts upside down and do not use a recoating mechanism. So recoating can be removed. Recoater can be removed when we use upside down. That means to say upside down setup. That means to say when we go build the object like this. So it is the layer grow or the layer are built in this, layer are built top to bottom. Okay. So after the vat is illuminated vertically upward through a clear window. After the system irradiates a layer, the cured resin sticks to the window and cures into the previous layer. The windowing platform pulls away from the window at a slight angle to gently separate it from the windows. So the advantage of this approach is in 3 folds. No separate recoating mechanism. See, you have also learned as and when you start introducing design for manufacturing, we have to reduce as many parts as possible. So if a coater subsystem itself can be removed, the life of the machine is high. So no separate recoating is there. The top vat surface being irradiated in a flat window, not a free surface, enabling more precise layers to be fabricated. The third one is going to be eliminating a regular vat. So the device process is done. So instead of having a supply on heavy demand material feed system, this can be used. The main disadvantage is small and fine features may be damaged when the cured layer is separated from the window. Mask projection photopolymerization. So this can be written as MPLSL modeling. So we have irradiance model and we have curing model. So for this irradiance model, incident beam characteristics is very important. So here we talk about lambda, we talk about power density, then we talk about frequency. Okay, then imaging system parameters, then we will have bitmap display of DMDs. So all these things are input parameter for irradiant model. From the irradiant model, the irradiant received by every point on the resin surface is got out, and from there it is led to curing. So you have to do first set of modeling and second set of modeling in order to get the true result of rapid prototyping, or to get the true result of the curing cycle. So here this comes to curing model. So in curing model we have to give an input of layer thickness. We also have to give time of exposure, because this time of exposure we saw this is directly proportional to the shrinkage, curing and other things. So this inputs are given, and finally what we get is going to be lateral dimensions of the cured layer. So this is very important. So for this we have to do irradiance model and cure model. In principle, however, it is easier to correct from these errors than in point-wise SL system. So in this mask projection, so here error correction is easy, important point, as compared to that of point, right, as point-wise stereolithography. The method called as compensation zone approach was developed to compensate for this unwanted curing. A tailored volume is subtracted from the underneath the CAD model to compensate for the increase in the Z dimension that could occur due to the print through. So using this method, more accurate parts and better surface finish parts can be achieved. So this mask projection model is going to give, or is giving, a better result in terms of part geometry, accuracy and surface finish. The next technique is 2-photon stereolithography. We saw 3: point-wise, then mask projection, then 2-photon. In 2-photon stereolithography, 2P SL, 2P, this is 2-photon. Photon is the pulse, is the energy packet. Light energy packet is nothing but photon. Okay, processes. The photo initiator requires 2 photons to strike it before it decomposes to form a free radical that can initiate polymerization. So 2 photons must strike it, decomposes to form a free radical that can initiate polymerization. The effect of this 2-photon requirement is to greatly increase the resolution of the photopolymerization process. Why? Because here we don't talk about layer by layer approach. Okay. It is true, since only near the center of the laser is the irradiance high enough to provide the photon density necessary to ensure that the 2 photon will strike the same photo initiator model. Feature size of 0.2 millimeter have been achieved by 2-photon stereolithography. 2-photon stereolithography was first invented in 1970 for the purpose of fabrication of 3-dimensional parts. This approach of 2 lasers were used to irradiate points in a vat of a photopolymer. So here the concept of layer by layer is not more pushed. When the focused laser spot intersect, laser 1, laser 2 intersect, the photon density was high enough to do photopolymerization. Most recently, 2-photon stereolithography receives research attention in the late 1990s. We will see the schematic diagram in the next slide. So here we use a high power Ti-sapphire laser of wavelength 790 nanometer, pulse width of 200 femtosecond, millisecond, microsecond, nanosecond, femtosecond, okay, and the peak power of 50 kilowatt. The objective lens have a numerical aperture of 0.85. Similar to the other micro stereolithography approach, the vat was scanned by a 3D scanning stage, not by a laser beam. The parts were built from the bottom up. The viscosity of the resin was enough to prevent the microparts being cured from floating away. This is also very important. The viscosity of the resin plays a very important role here to do this. Then complicated parts have been produced quickly by various research groups using this technique. So this is how a typical setup look like. You have a argon ion laser, you have a tie-sapphire laser. So this argon ion, tie-sapphire, it initiates, the photons are emitted, then you have shutter, it hits a mirror. So this mirror use the objective lens of objective lens with a numerical aperture of 0.85. So it tries to strike the objective lens. From the objective lens, it focuses itself to or it focuses towards the vat. Okay, so you have a lamp from here, and then you have a CCD camera to see what is going on in the curing cycle. Okay, so you have a computer from where the CAD data are inputted. So it is given to the stage for movement. So here is what is the photopolymerizable resin is there. So this is solidified resin is on the top. Okay, so this is this is on the top, and then you get it done. Okay, so these are the two lasers which we use, argon ion and tie-sapphire laser. This is used for doing 2-photon stereolithography, 2-photon stereolithography for micro parts. So CCD camera is only for visualizing what is happening. Okay, so we use an objective lens here of 0.4, but the objective lens from the mirror which goes towards the photopolymerizable resin is going to have numerical aperture of 0.85. So these are few examples which are done using 2-photon stereolithography. So it is a micro bull, so it is produced in 13 minutes. The shell of the micro bull was cured by 2-photon stereolithography, while the interior was cured by flood exposure of UV. So you see, you can use this too and you can cure it. From this, what can be inferred? From this we can infer that if you want to make micro parts for prototyping, okay, stereolithography can be very exhaustively used. And in stereolithography also, you can see whether to use a point-wise, mask type or 2-photon. 2-photon is going to give you very high resolution and make very small feature parts. If you want to make large parts, then you can always go for mask type, and you can also go for point. The mask projection stereolithography is going to give you good dimensional accuracy and large parts. In summary, photopolymerization process makes use of liquid, irradiation, curable resin called as photopolymers to fabricate parts. Upon irradiation, these materials undergo a chemical reaction and become a solid. So liquid becoming a solid, converted to a solid by light. Several methods of illuminating photopolymer for part fabrication were presented, including vector scan point-wise processing, mask projection, layer-wise processing, and 2-photon approach. The vector scan approach is used with UV laser in the stereolithography process, while DLP mirror array chips are commonly used for mask projection techniques, because in vector it will pass through an objective lens. So here in mask projection you will have a DLP, the galvo, you remember whatever we were talking about. Here you will have small mirrors, and these mirrors can be swinged to get varying masks made and projected on to the liquid. The 2-photon approach, which has the highest resolution, remains of research interest only. The advantage, disadvantage and the unique characteristics of all these three approaches were summarized. The photopolymerization process lend themselves to accurate analytical model due to the well-defined interaction between the radiation and the photopolymers. An extensive model for laser scan SL was presented, while a simpler one for MPSL model was summarized. So to recapitulate whatever we saw in this chapter, we explained why SLS is a good process to use to fabricate patterns for investment casting and metals. So whatever comes out of it, whatever you fabricate, it is a prototype. So this prototype can be used for making patterns, or the prototypes itself can be used as patterns. So it is called as direct tooling. Okay, or we can use this for making a mold, so it is called as indirect tooling. Explain why two photo initiators are needed in most commercial stereolithography resin. Explains what these photo initiators do. What do we understand by photopolymerization material? What are reaction rates? We saw about the dm by dt. Okay, explain the SL process overview, how to work with SL machine and SL scan patterns. What do we understand by the term vector microstereolithography? These are some of the points which we saw in this chapter. And now the task to students. So the task to students will be, try to take a photo negative, which in earlier days we used to say in ordinary analogous camera, so where in which we put a film roll, we get a photo negative. Try to take a photo negative and project the photo negative on the screen, right, using torchlight or whatever, using some light source, torchlight. Okay. See whether you get the same resolution of image when we move from center of the image to corners. Okay. 3. If it is same, then y. If it is not same, also tell me why. Next, try to take a polymer, okay, and heat it. Record visually what happens to the polymer over a period of time. Okay, and finally try to make a list of thermoplastic and thermoset resins and understand their structure. Okay. These are the homework, these are small assignments which students you can try, and this trying of these tasks will give you more insight about the process. The third question which I have posted in front of you is a very challenging question to answer, by the way. So you have to read lot of books and then try to figure out why is it. What I am trying to say is the image quality at this point will not be the same. If it is same, then why? If it is not same, why? So this is the film. Thank you very much.